Hi everyone, my name is Reza Hedayati and I'll be hosting actually the last session of 2024's Quantum Talent Showcase, uh, which is a bi-monthly series of presentations from quantum students and postdoc researchers at top universities, and is organized by QED-C's Workforce Technical Advisory Committee. This public event is a great place for presenters to have an opportunity to connect with the quantum industry and also industry organizations to find elite quantum talent entering the workforce. Today we have two great presenters. First up is Mr. Mykola Chernyashevskyy. He is currently a PhD student in the Department of Physics at the University of Pittsburgh. He has a background in cryogenics and electrical characterization for materials used in quantum computers and applications. The title of his talk today is Exploring Mobility in Zinc Telluride-Coated Indium Arsenic Nanowires. Second, we have Ms. Nora Bauer, who is currently a PhD student at the University of Tennessee in Knoxville, in the Department of Physics and Astronomy. She is studying quantum algorithms with a focus on using NISQ hardware to solve industry-relevant problems. She's particularly interested in quantum optimization and simulation for material science and chemistry. The title of her talk today is Simulating Neutron Scattering on an Analog Quantum Processor. Thank you very much. I appreciate both of you for presenting today, and I'm going to go ahead and hand it over to Mykola.
Hello, everyone. Let me just quickly share my screen here. All right, and then I just want to confirm that everything looks good. Is my presentation seen clearly? Am I sharing the right screen?
Yes, everything's good.
Okay, great. So, hey everyone, my name is Mykola. I just want to give you folks a little bit of a background on my journey. And I started off with getting a bachelor's of engineering physics at the University of Illinois at Urbana-Champaign with a minor in chemistry. I then got a post-baccalaureate internship at a company called Hypers Inc., where I focused on critical temperature measurements as well as doing some simulation work in the field of quantum sensing. After that, I transitioned to a contract position at Microsoft Station Q at Purdue University, where I worked as a quantum electrical characterization engineer. And then I moved on to pursue a PhD in condensed matter physics here at the University of Pittsburgh, where I'm currently at. I wanted to make something clear that very recently I switched out of the Sergei Frolov lab to that of Dr. Hrvoje Petek. But because the switch was so recent, uh, all of the physics that I'll show you and the project work that I'll be presenting was done when I was still part of the Sergei Frolov group. And it will be very similar to what I presented at the most recent APA's March meeting. So without further ado, let's dive into it. The work I'll be presenting here is the characterization I've done on nanowires that were grown at the University of Grenoble and the relevant PIs that were responsible for that was Dr. Hocevar and Dr. Palay Amalrich. And what you see here at the beginning of this presentation is an EDS false color image of a cross section of one of these nanowires on the left-hand side. And on the right-hand side, you can see a cartoon representation of what these nanowires look like. So there's a zinc telluride shell and an indium arsenide core. Now, I wanted to talk about some details regarding my motivation behind doing this research, and the motivation here is the search for Majorana zero modes. In order to better understand this motivation, we have to look into some theoretical density functional theory simulations that were done by my colleague, Dr. Malcolm Jardine, who at the time was a postdoc at Carnegie Mellon University in the lab of Dr. Nora. And The background I want to start with is just by saying that Majorana zero modes are theorized to exist at the ends of 1D topological superconductors. The semiconductor superconductor nanowires are a platform for 1D topological superconductivity. However, we run into some problems when direct superconductor contacts cause semiconductor band gaps to fill up. And on the left-hand side, density functional theory simulation, what we can see is that that indium arsenide band gap isn't very close spatially to the aluminum material contact. And the proposal of the project that I worked on was to use a high bandgap semiconductor, such as zinc telluride, as a tunnel barrier in these superconductor semiconductor nanowire devices. And you can see on the right-hand most side density functional theory simulation that this band gap is moved a little bit closer to that aluminum material contact. So let's just dive in a little bit deeper into indium arsenide and zinc telluride. The main takeaways of this slide are that both of these materials have a similar lattice constant. They have the same zinc blend structure, but one, and in this case zinc telluride, has a much higher band gap than indium arsenide. The next slide talks more about what folks over in Grenoble did when it comes to fabricating these nanowires. So on the left-hand side, you can see a cartoon representation to help understand what's happening inside of a molecular beam epitaxy machine used to grow these nanowires. But the process works as follows. Gold nanoparticles are spin deposited onto a substrate, and then both indium and arsenide are individually introduced into the NDE chamber, and the indium arsenide crystalline lattice grows faster around these golden colloids than the surrounding substrate material onto which the gold was deposited. The zinc telluride shell is then grown on top of the indium arsenide core once it's fully formed. The parameters for growth of both indium arsenide and zinc telluride are shown at the bottom of this slide. And the right-handmost picture is a photo taken of one of these zinc telluride-coated indium arsenide core nanowires after they've, completed fabrication. It's a 90-degree SEM image. Now, Dr. Sushen Tang of University of Pittsburgh also did some TEM analysis on these nanowires. What's interesting about that is that we see that zinc telluride shells develop crystalline facets, which are these hexagonal shapes around the round indium arsenide core. The shell thickness varies greatly between 4.1 and 10.7 nanometers, depending on how you measure it from the indium arsenide core. And no apparent defects were observed from cross-sectional imaging, which can be seen on the right, which suggests that there's perfect epitaxial growth of zinc telluride from this indium arsenide core. Our collaborators in France also took some scanning electron microscopy results, and it was shown that there were stacking fault defects observed at the top and bottom of these nanowires. And the conclusion that we draw from this observation is that the middle of the nanowire is best used to fabricate devices out of them. And so, speaking of fabrication, we move on to the part of the work on the project that I did, which is fabricating gate-tunable two-terminal devices out of these nanowires. And on the top right-hand side, you can see a cartoon representation of what that looks like. Please note that there's an insulating layer of oxide that exists between the silicon substrate and the nanowire itself. And the details of the procedure are as follows. I used the micromanipulator to place wires onto silicon p-doped substrates. And argon milling was used to remove the zinc telluride shell at the side of the contacts, and titanium and gold were vacuum evaporated to make actual contacts to these nanowires. The bottom right-hand picture shows an SEM image of what a typical device would look like. And on the left-hand side, you can see some of the parameters that were used for both the argon milling as well as vacuum deposition. Now, after fine-tuning these fabrication parameters, I got some preliminary results. Before showing them, I wanted to talk about how these measurements are completed. So the procedure is as follows. We first cool these devices to 4 Kelvin in a liquid helium bath. We bias the source and drain with a voltage, and then we run backgate scans while measuring current. And so the circuit for that is shown in the top right-hand side of this diagram. We use the equation shown on the left-hand side to extract mobility, threshold voltage, and contact-to-contact resistance. And the left-hand side bottom diagram is an example of a pinch-off curve that gets run on of some of the data we would extract, we would collect from measuring these nanowires, as well as a sample fit curve that's used to extract parameters that are highlighted in purple. And so without further ado, let's move on to some of the data I got. What you see here is 6 sweeps demonstrating both the pinch-off and the saturation region of the indium arsenide core of these nanowires. We can see that there's hysteretic behavior present depending on the direction of the backgate sweep. So you can see the arrows that show whether the sweep is being done to the right or to the left on the diagram. The hysteretic behavior is consistent. So that means that there's little dispersion, and the sweeps are basically right on top of each other. And the direction of the sweep also influenced the transport values that we extracted. So you can see the direction would influence both the mobility, the contact-to-contact resistance, as well as the voltage threshold of these nanowires. Now, this slide shows another device that we measured, and we can see that it's able to pinch off, demonstrate hysteretic behavior. However, the data fit code that we use to extract transport parameters fails to extract them. And so the takeaway here is that, you know, we needed to get more measurements on more devices done to get better statistics on what's going on, which leads me to sort of my conclusion. And just to run over, just to summarize my presentation really quickly, the growth was done using vacuum liquid solid methods in a molecular beam epitaxy. The TEM results showed that there was good epitaxy. And then the SEM results also showed that the middle of the nanowires were best for creating devices. My job was to fabricate gate tunable 2-terminal devices. And preliminary results showed hysteretic behavior, and we were able to extract some parameters. The next steps were to measure mobility of more of these zinc telluride indium arsenide devices, measure mobilities of just pure indium arsenide for the devices that were, nanowires that were fabricated with no shell, and then also measure the mobility of varying zinc telluride shells and 4-diameter devices. Finally, after doing that preliminary characterization, it would require to use, for us to, moving on with the project would require depositing either aluminum or tin to act as a superconductor on these nanowires. And that basically sort of concluded my project and the work that I did before I switched labs. So if you have any questions, please feel free to ask them now.
Thank you, Mykola. I have a question for you. What challenges have you encountered when fabricating and characterizing your devices?
So the challenges that I encountered are encountered in my supplement section. One of the challenges that I encountered with this particular project is argon milling. So I had to fine tune the amount of time each that I would have to mill these devices and find the best time to argon mill them, which required creating as many devices as you see in this Excel sheet to the left-hand side, and then find the one that and find the argon milling time that produced the least dispersion and room temperature resistances, as well as the lowest room temperature resistances I could find, which was, according to my data, around 4 to 4.5 argon minutes of argon milling.
Great, thank you. Any other questions before we move to Nora?
I have one.
Yes.
And this just could be because I am I feel sometimes like I have the memory of a goldfish. How will this what does this do for industry, right? Like, where is the commercial application for this?
I think in terms of industry, the things that my opinion on it is that is more of like the development I had as an employee. So I gained a lot of nano fabrication skills. So these could be applied to fabricating more direct quantum computing devices such as qubits or resonators or things like that.
Okay.
I use the same exact equipment used to do those. And then in general, the field of physics in which I worked at the time in the Frollo lab was called quantum transport. So it was a quantum related field.
Okay, cool. Thank you.
Yep.
All right, well, thanks again, Mykola. Appreciate
Yep.
it. Nora.
Thank you.
Over.
Got it. I'll stop sharing now.
Okay. Can everyone see this all right?
Yes.
So good afternoon. My name is Nora Bauer, and I'm a PhD student at the University of Tennessee, Knoxville. Today, I will be talking about our recent work, just published on arXiv last month, simulating neutron scattering on an analog quantum processor. I'd like to thank my collaborators in quantum algorithms at UT, and also those who work at Oak Ridge National Laboratory on neutron scattering characterization of materials, who were critical in the conception of this work. A brief outline. Our high-level goal is the characterization of entanglement in materials via the quantum Fisher information, and more importantly, establishing a workflow between neutron scattering experiments and quantum simulation. So I'll discuss how analog Hamiltonian simulation is the ideal technology for this work, and why we chose to study the transverse field Ising model. Then finally, I will have a brief aside to discuss error mitigation before providing our results, and an outlook that details our next steps. So characterization of entanglement is critical for the identification of materials and systems relevant to quantum technologies. And the quantum Fisher information, or QFI, is of emerging significance because it allows for quantification of multipartite entanglement as opposed to other entanglement witnesses. So using the QFI FQ, which here the tilde signifies normalized QFI, but we'll use both. We are able to establish lower bounds for k+1 partite entanglement in a system of n particles. So if we want an example, we can look at the GHZ in the qubit GHZ state, which is maximally entangled. So you can see that the GHZ state saturates the entanglement bound here at each n. And there's also this n-scaled scaling of the QFI as you increase the system size of the GHZ state. So is n squared for a maximally entangled state, but more generally, the scaling of the QFI with system size can be used to indicate criticality in condensed matter systems. The QFI is also relevant because it can be obtained directly from the dynamic structure factor, DSF, or the dynamic susceptibility as they're related, which is measured during neutron scattering. The QFI at zero temperature is obtained via a direct integral over the DSF in frequency space. And for our case, just a note, we will also use the form with only the Z component SDZ as you would obtain in polarized neutron experiments. So in neutron scattering, incident neutrons with wave vector k and frequency omega are scattered off nuclei, and the intensity of the outgoing neutrons with reduced energy is measured. This DSF is related to the retarded Green's function in frequency space. So At the lowest level, what we can do if we would like to simulate this is measure the space-time Green's function, then Fourier transform to get this frequency wave vector space Green's function. You can see that this space-time Green's function, the base level is an out-of-time correlator between the spin variable on atom I at time t and the spin variable on atom j at time 0. So you can see that if you wanted to simulate this, a good place to start would be to be able to do this time evolution to compute these exactly, or use some sort of Krylov space method to compute these values for the Green's function. So this brings us to an important branching point. So if we want to be able to compare experimental results with theory, we need an efficient way of computing the DSF for various Hamiltonian models. And generally, these systems can be either in more than one dimension, or be thermal states, or be out of equilibrium states. So we need a computational method that can handle all of these complications. First, we can consider the classical methods available to us. So the most commonly used method today, and the method that is currently used by our collaborators, is DMRG, density matrix normalization group, or their tensor network methods, where the Hamiltonian is diagonalized in the Krylov space and used to compute the energy levels required to measure the DSF. Here they generally get a very good approximation, or they can even obtain the exact result. However, this works well for one-dimensional systems, but begins to struggle in 2 dimensions and highly entangled states. So this is the place of failure that we're wanting to work into with quantum computing. So there's also quantum Monte Carlo QMC methods, but they encounter the sign problem in many systems, so they're not widely applicable. You could also include Lanczos methods here, but usually those are restricted to smaller systems or toy models. So now we can also look at the quantum methods that are available to us. So the most natural attempt is to approximate the time evolution as a Trotter series on a gate-based device, like what is offered by IBM or Quantinuum. But this requires deep circuits to memorize Trotter error, which are generally not reasonable for NISQ hardware with the error rates we have today. We could also consider quantum imaginary time evolution, kite algorithms, but this requires optimization over many steps and introduces a large overhead. And so the focus of this work is analog Hamiltonian simulation, which we find to be an efficient and scalable approach to this problem. So the main switch for using analog quantum hardware is moving from a gate-based quantum computing paradigm, where the operations are implemented as circuits made up of some fixed gate set, to a pulse-controlled model where the system is evolved by a time-dependent Hamiltonian. So this is a natural choice for time evolution simulation, but if we would like to do other algorithms, particularly state preparation, we need to specifically formulate these for analog hardware. For this, we consider QEra's Aquila device, which is publicly available on Amazon Web Services, AWS. Aquila features 256 qubits, which can be placed in an arbitrary geometry in 2D space. For example, here's a world map. You can place these anywhere in this XY space. The qubits are defined as Rydberg atoms, and the computational basis states of these qubits are defined with 0 being the ground state of the valence electron and 1 being the excited Rydberg state of the valence electron. So the evolution of the system is defined by the Hamiltonian given here. The user can choose the functional time-dependent forms of the detuning delta, which is the on-site term that balances the ground versus excited state occupation. You can see that in this Hamiltonian, this detuning is actually a local parameter on each atom. This is because QEra recently released an experimental local detuning functionality, and it has some constraints, but this ability to do local detuning operations will be critical to how we measure the DSF. There's also the amplitude or Rabi frequency, which is a global parameter, which is the hopping term between the 0 and 1 states, with this phase controlled by phi. Additionally, the atoms have a constant term in the Hamiltonian known as the Rydberg interaction, which provides a strong distance-dependent energy barrier between two one-state excitations close to each other. So the user can choose the positions of the atoms in 2D space to effectively tune this entangling interaction between qubits. So if we were to consider how this repulsive force is going to act, we can see that 2 excitations near each other would be energetically unfavorable. So if we were to put 10 qubits in a line, we would likely have alternating excitations. So ground Rydberg, ground Rydberg. So we say that the transverse field Ising model, the TFI, in the antiferromagnetic case is the ideal case to start simulating using these Rydberg atoms. So we can make this a bit more formal. If we have our Rydberg Hamiltonian with the atoms positioned on a chain, then by fixing our detuning, amplitude, and phase values as shown here, we can realize a very close approximation to the TFI Hamiltonian. The main error comes from the long-range nature of the Rydberg interaction, because this sum really goes over all qubits. So there will be contributions from next nearest neighbors, and especially if we don't have enough room to put all the qubits in a line, and we need to do some sort of arc or something, there'll be additional energy contributions, but it goes as r to the -6, so it's fairly small. So we can obtain a very close approximation of real-time evolution of the TFI Hamiltonian. So this being able to time evolve is a key step in computing the Green's function. We can see from this form written here in terms of time evolution. So if we wanted to do this in sort of a naive way, well, we'd say if we want to compute these expectation values, we start with the ground state, we apply, this first Z operator, we time evolve, apply another one. But then at this point, we would have to reverse time evolve. And this is, since we can't flip the sign of the Rydberg interaction, and that's fixed, we can't reverse time evolve. However, Raman spectroscopy provides a solution for us that we can implement. And there are more details about this in our paper, but I'll just give a brief summary here. So we can prepare the ground state of the system, psi 0, and then we apply this specific perturbation on atom J. So this is for measuring the GZZ Green's function. We would apply this pi/4 rotation on atom J using local detuning. And then we would time evolve and then measure. And when we measure in the Z basis, the Z expectation values actually correspond to the Green's function. So note that this is not, so if we wanted to measure GIJ, Green's function, we would apply this local perturbation on atom J and then measure qubit I, and that would be our result. And I should note that this direct relation between the Z expectation value and the Green's function is not a general case. Usually there's a few other terms here, but in the case of the transverse field Ising model, those other terms actually cancel out. So we have this direct relation. Okay, so what of this can we do? The measurement in the Z basis is the default measurement you do on Aquila because that's the computational basis, so we can do that. We already have established real-time evolution on Aquila using the very close relation to the TFI model. And then we would use Aquila's local detuning capability to perform a local Z rotation using this local detuning. And I should note that there's, we're going to use the center side approximation if you're familiar with this, so that we only apply the perturbation on a single atom. And then in our Fourier transform, we use an approximation to get the actual DSF. So now we're left with this, the last step is to be able to prepare the ground state of the transverse field Ising model on this analog device. So the first thing we did was try a quantum approximate optimization algorithm type ansatz, which is QAWA. And the main constraint here was that we only have 4 microseconds to evolve on the Aquila hardware. So that we ended up needing too many levels, and switching between these alternating pulses introduced too much noise, and it wasn't effective. So we decided to use an adiabatic type ansatz with these ansatz for for global amplitude and global detuning. And they have the functional forms given here in terms of these hyperparameters P. And this is a plot of the amplitude and detuning before and after optimization. So we optimize these hyperparameters with respect to the overlap with the ground state, or if we would like to do it in a way that's a bit more tractable on hardware, minimizing the measured energy, the TFI model. And then we can obtain reasonable ground state fidelities with this ansatz in these smaller systems that we can test. However, the main benefit is that the values of these hyperparameters appear to converge to fixed values as we increase the system size. So this is a nice indicator of scalability because it becomes difficult to perform calculations for larger systems. So, for example, later on when we do L equals 25, we can't do that easily just on a normal computer. So we extrapolate the values of these hyperparameters to larger L values, and then use those, and those provide a close approximation to the real ground state. Okay, so now we have all the pieces we need to prepare the ground state, apply the perturbation, time evolve, and measure. So the last consideration, which is something we always have to consider when working on today's quantum hardware, is error mitigation. So since Aquila is a noisy intermediate scale quantum or NISQ device, we will obtain noisy results after running our circuit or pulse program as shown here. So this is the space-time Green's function at time equals 0, and you can see this noiseless black line of what it should be, and then this noisy red line that deviates from it is what we would actually measure. So in order to be able to test error mitigation schemes and ways to correct for this, we developed a realistic noisy simulator of Aquila. This was inspired by work done using a different Python package in Pulsar. We implemented this in PennyLane. So we first include state preparation and measurement or SPAM errors. So measurement errors are incorrect identification of Rydberg or ground states that occur with some probability. So false positives and false negatives of being in the Rydberg state. And the values for these probabilities are actually provided by QED-C. State preparation errors occur when there are missing qubits in the register. And then we also include laser fluctuation errors, which include detuning shifts due to atomic movement. And it also includes the fact that the laser that provides the Rabi frequency actually has a finite width. So instead of being a constant value, it's more of a normal distribution. So atoms away from the center of the field would have lower amplitudes, and we also included just general fluctuations in the amplitude from laser inhomogeneity. Then finally, we included effective noise channels described by these cross operators here, where we include depolarizing and qubit reset noise. So the goal is that we would like to be able to test out multiple types of error mitigation and then use the best one actually for when we run on hardware. And we would also like to be able to provide corrections based on characterization of the noise. So these space-time Green's function values before proceeding with the calculations, like the Fourier transform, so that we can correct for that and then move on with our calculations. So we were able to test various error mitigation strategies and had success with this noisy estimator scheme shown here. So we replaced this expectation value of the Z operator with this noisy estimator Z script, which involves the survival of the computational basis state G script, which can be measured using randomized measurements on the hardware or noisy simulator. In this case, we measured it on the noisy simulator. So this allows for hardware-specific noise characterization because we end up with this vector of G script values that correspond to each qubit. So if there are qubits that are very far from the center and have a large amount of error introduced, then those would have a different GJ value than ones that are less noisy. So this, you can see that in the noisy simulation and noisy calculation of G-script vector that we were able to provide a significant mitigation of the error. So here we have the measured DSF value for the noiseless case, which is green, and noisy, which is blue. And then when we apply the error mitigation for purple, the mitigated and noiseless values are nearly indistinguishable, especially in this peak here. The other benefit that we saw is that the G-script values at time 0 still provide nice error mitigation results for non-zero times t. So we can get away with only calculating this once, and that's really beneficial because those systems are going to be easier to simulate than the time-evolved system. So if we can, get good estimates at t equals 0, then we can apply that later on for doing complex time evolution. And it really just describes a bias in the Z expectation value, so that makes sense. The finally to our results. So we performed this on the experimental Aquila hardware. Aquila has a maximum evolution time of 4 microseconds. So we ended up using 2.5 microseconds to prepare the ground state and apply that perturbation. And 1.5 microseconds was used to do 15.1 microsecond time evolution steps. So each time we would measure and then use this in the Fourier transform to get the DSF. So here's our case for L equals 11. We were able to compute an exact DSF over this time range and use it to optimize the G script vector. In this plot, this red line is the raw measured values, and the green line is the error mitigated values with some error bars on there. The blue dashed line gives the value with the approximate state preparation using the adiabatic method and exact time evolution. So this shows that since we're starting with something that that has a fidelity not equal to 1, this is like kind of the best case of what we're going to be getting if we do the time evolution well. And then the black line gives us exact value from just state vector calculations. However, 11 we can compute exactly. So naturally we want to scale this up to something to a larger system that can't be computed just using state vectors easily. So we choose L equals 25. Here we compute the comparison using DMRG and MPS evolution and use the G-script vector extrapolated from the L equals 11 case. So here again, the red is these raw measured values, the green is the mitigated, and the black is the DMRG, so we can see nice agreement with the DMRG values. Okay, and finally, since our initial motivation was the QFI entanglement witness, we can use our measured DSF to compute the QFI experimentally. We can compare the values to the threshold values for K+1 partite entanglement in the system. So for L equals 11, we observe bipartite entanglement with the mitigated values. So the red's raw, and then this is the K equals 1, so that's bipartite entanglement threshold. Then we have a mitigated value and analytic is an exact calculation using a different formula for the QFI. And for L equals 25, we obtain 4-partite entanglement in the mitigated case. So you can see that mitigated case is within an error bar of the DMRG value and hits the 3+1 4-partite entanglement bound. We can also see that we have at least bipartite entanglement in the raw case, which is important because it shows that even without the error mitigation, we're still able to observe entanglement in the system. Okay, so finally for some next steps. In the near term, we're currently working on moving to the 2D Ising model because, of course, this 1D case is a proof of concept and trying to understand, where the problems will be. But we want to quickly move to systems that are more difficult to simulate with classical methods, notably DMRG. We're also working with our neutron scattering collaborators to identify models that correspond to materials they are currently studying, because ideally they would have some system, for example, some sort of Ising type system that has certain couplings that aren't really known, and they would be able to propose what the system would look like. We would be able to do a calculation of the DSF with those couplings, and then we use it to compare, and we can work together in this way. So we're interested in moving closer to the actual materials they're working on in the lab today. Even further, we're interested in out of equilibrium systems and thermal systems, since these pose additional problems for classical methods and might require alternative algorithms such as kite for state preparation. So particularly, there are some interesting scaling properties of the QFI as a function of temperature, and we would like to test the performance of the kite algorithm to prepare those thermal states and then do this QFI procedure as implemented on Aquila. We are also working to identify systems beyond the TFI model that could be studied. And thank you for your time and the ability and the opportunity to share this research. I'm glad to answer any questions. This is my email, and this is the archive number for our paper that has a lot more details in it. So thank you, everyone.
Thank you, Nora. Are there any questions for Nora?
I have one if there's time.
Go ahead, please.
So how do you compute your Fourier transforms? Is it, the FFT function that one would find on MATLAB, or is it something more exotic? Computational method.
Yeah, it's actually we use the center side approximation. So really, it's just ends up being two integrals over space and time to get the value in terms of frequency and wave vector k. So yeah, we use the center side approximation because this really cuts down the amount of quantum resources we need, and it's pretty standard. Even our collaborators use the center side approximation in these systems, especially the larger ones, for doing when they do their DMRG calculations.
Thank you.
Nora, does your work have a path to quantum utility or quantum advantage?
Yeah, so this one we're really working to try to fill in the gap where DMRG and tensor network methods start to fail. So that's our main goal. So that's why we started in something that's one-dimensional, but really we can't do three-dimensional in the system now, but working in 2 dimensions and trying to really push the envelope of what DMRG can do effectively and try to get closer to where it begins to fail is our main goal. Because we have 256 atoms on here, so if we could find a way to compute prepare the ground state and do the time evolution effectively, this should start to push the boundaries if we're using systems. For example, time evolution they actually don't use time evolution in the DMRG. Our collaborators they use this Krylov space method, but highly entangled systems and systems in 2D start to fail, or at least require more resources as we increase the size and go in 2 dimensions. So that's really our goal, is trying to find where DMRG and tensor networks start to fail.
Very good, thank you. Are there any other questions? Okay, if not, thank you very much for your time. We're gonna get done quicker than normal. But I appreciate again. Thank you, Mykola and Nora, for your presentations, and have a great day. Thank you.